Hi there and welcome back to this course in ABE153, and this video will be talking about materials and specifications. For the context of this presentation, we'll first discuss the overall classification of materials, and then we'll talk about the standards and specifications, and then we'll have a detailed discussions about carbon steels, tool steel, stainless steel, cast iron, aluminum, copper, nickel, cements and glasses, polymers, and elastomers, and lastly the composite materials. Uh, by the way, the detailed discussions for this type of materials, you have already taken that in the material and processes course, or maybe basic of materials engineering and sciences or things like that. So right here we're just gonna have to run through the different types of materials, but our goal is we want to apply this in mechanical design. So we need to have a knowledge on the available, let's say available shapes or available sizes, as well as the properties of materials and the designation. Okay, so to start, engineering materials, they are classified as either metals, ceramics, polymers, and composites. And for some references, it says here ceramics and glasses, or they separate the glass from this ceramics. So um, this is additional classification of materials. And also for polymers, they also separate elastomers. Okay, so right here the glasses, it's under the ceramics, but in some references they they separate this, okay, these glasses, and also the elastomers. So they have like 1, 2, 3, 4, 5, 6 classification or classes of materials. Okay, anyway, the ceramics and glasses could have similar properties, so that's why in some references they're just one classification. And also for polymers and elastomers, they're not actually the same. They don't have the same exactly the same characteristics or compositions, but somehow they are more related, as compared to, let's say, metals and composites, for example. Okay, anyway, for metals, these are type of materials that they are characterized as having high moduli and also ductile. Okay, not every metal is a or not every metal has a ductile behavior, because for some steels, like higher carbon steels, they don't have much ductility, but generally they can be classified as materials having a ductile behavior. And when we say ductile behavior, that refers to the, if you recall, in our stress strain curve. Okay, so we have this stress strain curve for steel. So from this point to fracture, okay, from yield point to fracture, that's what we call the plastic deformations. And when we say high moduli, recall in the Hooke's law equation that the force is directly proportional to the deformation or deflection, and the proportionality constant is this k. Sorry, so I think this should be written F is equal to kx, or k this delta, okay, where k is the proportionality constant, and that refers to the stiffness. And when we say stiffness, if a material has higher value of stiffness, then that means that you need much force in order to deform the metal, or in order to elongate the metal in terms of let's say tension loading. Okay, so if you have low stiffness, then even at low loads, you can have deformations already. Okay, and another characteristic for metal is that it is prone to corrosion. Okay, and that's a degradation of material. So once it is exposed to the atmosphere, to the oxygen or atmospheric condition, then it can corrode. Okay, furthermore, metals can be classified as either ferrous materials or non-ferrous. And when I say ferrous materials, basically it contains iron. So example of that is steel, cast iron, and many alloys, steel alloys. And for non-ferrous materials, that refers to metals that doesn't have iron in their composition. Okay, so let's move on. For ceramics, this is a type of material that's characterized as brittle, or that has a brittle behavior. And for brittle behavior in this stress strain curve, okay, so instead of having this plastic deformation, it has just something like this, and then it fractures. So no plastic deformations for brittle materials. Okay, so example of these are glasses and concretes. And what else? They can also have high moduli. And moving on, for the polymers and elastomers, they're another class of materials that's actually in the other end of spectrum. Okay, because they have um, low moduli, so that means that they can exhibit large deflection, if it's just at low loads. But somehow their advantages is probably in terms of uh, cost in terms of material itself, plus the cost in terms of processing, in terms of the processing the material. So they have that advantage over the metals and the ceramics. But of course, it's just limited to just some certain temperature ranges. By the way, for ceramics, another advantage of ceramics is that it is not, or it is resistant to corrosion and heat. Okay, so what that means is that if it is resistant to heat, then the application is that, for example, you have equipment or machinery that operates in high temperature, then probably we would need ceramics, ceramic linings or things like that. Ceramic linings in terms of furnaces. But the problem for these ceramics is that they don't have that strength. Um, they don't have that strength as that of the metals. Okay, so sometimes it's gonna be a mixture, or it's gonna be a composite material, a combination of metals or ceramics, or there are also materials that are being developed under these composite classifications. So composite classifications, they are a class of materials that's actually a combination of the other three. And when you combine those materials, they provide a superior properties as compared to the individual classes. So example of this is carbon fiber, and another one is the cermet. So the combination of ceramics and metal. Okay, and there's still a lot other. Okay, so now let's move on to the standards and specifications. Standards and specifications are documents that describe and or recommend a set of rules and conditions for how materials and products should be manufactured, defined, or measured, or tested. Okay, so the main goal of this standard is for compatibility, and we have here the different organizations or or associations that sets forth the standards. And one example is the AISI, that's the American Iron Steel Institute, for the SAE, the Society of Automotive Engineers, and ASTM, this AA or Aluminum Association, and there's actually many more organizations as we go along in this course. We'll also encounter um, other other standards. Okay, so we need to to understand this because some of the materials they are specified, let's say in terms of these standards or in terms of this standard ASTM, or let's say AISI, or for bolts or whatever. Okay, so by the way, recall that in our structures engineering course that uh, in our topic on steel structures, we are using the ASTM standards, but for mechanical designs or in this course, we'll be using much of these specifications or designations, AISI. Okay, now let's start with these carbon steels and its alloys. So probably we can say that carbon steels, they are the most common metal with wide range of applications, and also they have wide range of properties through composition, and it can have um, the properties can be changed through heat treatment or mechanical treatments. And right here the typical shapes or sizes, they are available in plates, sheets, strips, bars, wire tubes, castings, and forgings. Right here we have links about steel beams, steel plates, and steel sheets, and let's try to check this out. Okay, so that's an example of a steel beam. Okay, another one is steel plates. Okay, so right here, this is a plate, example of a plate. So the difference between a plate and a sheet is that the thickness, this thickness, if it's roughly, let's say 6 mm or 6.35 mm, that depends upon the references. Okay, so let's say if it's 6 mm or greater, that's referred to as plate, and if it is 6 mm 6 mm and lower, that's going to be referred as sheet. Okay, and for the steel sheets, we have here, right here it says we have hot rolled sheets or cold rolled sheets. Basically it just refers to the additional processing done, or let's say mechanical treatments done for these steel materials, and there's gonna be changes in terms of properties and also in textures. So right here you would notice some irregularities in textures in these hot rolled sheets, but for cold rolled sheets they are characterized as having a smooth surface finish, and they have higher strength. Okay, and we can also have galvanized sheets, like for example additional coatings or additional compositions that adds resistance to corrosions. Okay, and going back in our presentation, now let's define what is a steel. Steel is basically an alloy of iron and carbon, and having a carbon content ranging from 0.15 to 1.7%. Okay, so take note of these limiting values. That depends upon the references, because for some references they use like 0.3% or 0.2%, and right here their upper ranges is something like 1.6% or 2 point something. So that depends actually, but at least you know the ranges. Okay, the typical range. Now let's say it's the lower value is 0.15 and the upper value is 1.7. So if you have a carbon content by weight, because in this figure we have this arrow line which which designates the, or which corresponds to the carbon content by weight. So if the steel, if the carbon content is within 0.15 to 1.7, so that's referred to as steel. And anything below the lower value, that's referred to as wrought iron, and anything above is referred to as cast iron. And right here we have two arrows, one for the strength and one for the ductility. Okay, so right here it says, you can see it here, that if you have an increasing carbon content, then the strength is actually increasing. So you have a stronger steel, but in terms of ductility, you have a lower ductility. Okay, there are applications actually that requires less ductility but higher strength, like for example gears or tool materials for tools. Okay, so you don't want a material that deforms easily for that type of application. But for this end, for this composition, now we want a higher ductility, even though we don't need much strength. Okay, so typical application for this is for those materials or applications for, let's say, press, like sheet metal press, stamping or things like that, or the car body shapes. Okay, so we want deformations, we want a material that can be formed easily, right? So that's why we have this higher ductility choice of material. Okay, so moving on, we have this classification of carbon steels and its alloys. So we have low carbon steels, medium, and high. So let's focus now on these three, because these two right here is something like additional, due to additional composition. Like for example, if it contains sulfur sulfur and phosphorus, and it's referred to as the sulfurized carbon steel. And right here there's let's say high strength low alloy steel, that's HSLA, so low carbon content but with improved properties. Okay, so let's talk about low carbon steel, medium, and high. Okay, when I say low, it's basically a type of steel having a carbon content less than 0.3%. And if it's medium, that's 0.3 to 0.5, and if it's high, then that's greater than 0.5. Okay, so typical applications for low is components requiring ductility and not strength. So as I have mentioned already, this example is, for example, the car body shapes, or materials where we need or materials where we need to be, where we need the formability. Okay, so we can form it easily, okay, rather than strength. But for medium carbon steels, where we want much strength or higher strength, then the typical application are gears, axles, connecting rods, and much higher carbon steel, that's drills and cutting tools. Okay, now for the AISI and SAE designation for carbon steel. The SAE classification system for alloy steels uses 4 or 5 digit numbers. So right here we have a 4-digit number, and for the first digit, that refers to the alloy group, and that indicates the major alloying elements. Like for example, if it's 1, then that's carbon steels, and if it's 2, that's nickel steels, and so on and so forth. Okay, so you would notice this actually, or you would find this in some of the past provisions regarding, let's say, molded plow, or the steel shafts that says AISI 1020 or 421 something. Okay, so this is the meaning, or this is the interpretation. So again, the first digit refers to the major alloying elements, and if it's 1, then that simply means it's a plain carbon steel. And the second digit refers to the specific alloy group. Okay, so for the 0, that's plain carbon, meaning no modification. If it's 1, then that's resulfurized, and 2 or 5. And then for this last 2 digit, that's the carbon content. in 1 over 100%. Okay, so that's 1 over 100%. Okay, so for example, we have a Si1020. So the first one refers to carbon steel. The second one refers or means that it's a plain carbon steel without modification. And for the last two digits, that's 20 divided by 100, right? So 20 divided by 100, that's 0.2% carbon content. Okay, so you would notice that our range is something like 1.5% to, sorry, that's 0.15, 0. Right, 0.15% to 1.7%. Okay, another example is ASI 4140. Since it's 4, then that means it's a chromium molybdenum. For 1, that's 1% molybdenum. And for this last two digits is 40 divided by 100. This is 0.4 carbon content. So the meaning is that a chromium is a chromium molybdenum alloy steel containing 0.4% carbon and about 1% of the major alloy molybdenum. Okay, there's also another specification for steel using ASTM. That's for example A36, A325. This one is typical for plates and some shapes. That's the type of steels, and for bolts we have A325. Okay, and as I have already mentioned earlier, that for mechanical applications, or let's say mechanical design applications or specifications, it's what's usually used is the AISI. But when we're dealing with structures, well, this is more common. This designation. Okay, and right here it says that the designation consists. Okay, take note, in its simplified form, the letter A, that which stands for ferrous materials, and followed by the arbitrary numbers. Okay, so there are a lot of shapes, standard shapes, like for example S shape, W shapes, hollow steel sections, and things like that you have already encountered in your structures engineering course. Okay, the next one is the tool and die steels. So tool steel contains various amounts of other elements, like for example tungsten, molybdenum, cobalt, vanadium. And compared with steels, tool steels are very hard with high yield strength. Okay, so its hardness, resistance to abrasion, and ability to retain shape at increased temperatures are the key properties of these materials. Okay, so as the name implies, these type of steels, they are designed for the cutting tools, punches, dies, molds, and machinery parts. So let's check our link right here. So example of tool steels, it looks like this. Okay, so can have these bar sections, square or many other sizes, and probably other shapes. And if you want to read this, okay, this article, then you can just check this website. You can check their website. Okay, and for the classification of the tool and die steels, we have high speed steels, hot work, cold work, shock resisting, molded, special purpose, and water hardened. And for the symbol, it has here M, T, H, and so forth. And here is the major alloying element, like for example M. If the symbol is M, that's molybdenum. That refers to high speed steel. And for the AISI number, it can be M2, M10, M42, and right here is the typical applications. So you can just read it in our lecture handouts. Okay, moving on. The next material is the stainless steel. Okay, stainless steels are characterized primarily by their corrosion resistance because of high chromium content. Okay, so this is the characteristic for stainless steels. So they have high chromium content, and the minimum value for chromium is 10.5, but typical ranges are or is 10 to 18%. And they are cold stainless because in the presence of oxygen or air, they develop a thin, hard adherent film of chromium oxide that protects the metal from corrosion. Okay, so right here in this link, there is okay, so in this figure, it shows a corrosion of steel. But if you have a high chromium content, okay, so you have this iron plus carbon plus chromium content, then this chromium, once the chromium content in the stainless steel reacts with oxygen in the ambient air, and it forms a protective layer, and that layer is chromium oxide. Okay, so that's why it becomes resistant to corrosion. However, once this layer is damaged, then it can also start to damage the material. And so right here we have example of 316 stainless steel sheet, or 304, and also the finishes. Okay, so let's check this out, the 316. Okay, so 316 stainless steel, and another one is 304. Okay, so they have this different finishes, and right here. Okay, so in this website, it shows the different finishes for stainless steel sheets. So we have here the number 1, the 2B, number 4, also the hairline or the mirror type. Okay, now let's move on to the types and designation of stainless steel, and it uses this AISI or SAE designation. So we have here the types that's classified in terms of austenitic, ferritic, or martensitic, and there's also another 2 right here that gives another, probably due to development, then they exhibit different properties from this basic. Okay, so in terms of series, so it's classified as either 200 series or 300 series or 400 series or 400 and 500 series. So in terms of types, the characteristics is for austenitic types, it has a moderate strength and non-magnetic, but excellent corrosion resistance. Okay, and this type, or let's discuss it here. For austenitic type, the typical applications is the food processing equipments, and if we are or if the application is heat exchanger, tubing, furnace parts, and things like that, then probably we would need 400 series. And for turbine engine parts or pumps, then we would need 400 or 500 series of martensitic types. Okay, so in terms of characteristics, the stainless steels, they are substantially different from those of carbon or alloy steels and other metals, because most stainless steels types are tough and rather gummy. So you would feel actually the difference when let's say when you're bending or when you are cutting the stainless steel versus the carbon steel, even with the same thickness, or let's say 1.5 mm of stainless steel and then another 1.5 mm for a carbon steels, you would actually notice the difference. So for stainless steel, it's like it has this gummy behavior. And also in terms of welding process, then the welding rod that is compatible for stainless steel is different than the welding rods used for carbon steels. Okay,